Hi, I'm Ben-Yaakov. This presentation is entitled Saturation Region in BJT and MOSFET Transistors, an Answer to Riddle. Now, the riddle was related to two articles in Electronics Tutorials website, and here are the links to them. And the riddle itself is given here at this video that I've posted earlier. I'm going to put these links at the page, at the YouTube page of the video that you are now watching. So this presentation now is related to the question of saturation region in BJT and MOSFET. I'm going to give a background and then go back to the riddle and give my answer to the riddle. So the riddle was related to a MOSFET, the operation of a MOSFET, the region of operation, and its operation as a switch. Here we see the output characteristic of a typical MOSFET, and here when it is operated as a switch, and there are some explanation. I'll go back to the details later on after sort of covering the basics of saturation in BJT and in MOSFET, and then I'll give my answer to the question, find at least 3 errors in the above explanation, and this is the explanation in the Electronics Tutorial website. So let me start off with the background and some definition of saturation region in BJT and MOSFET. So in BJT, this will be the output characteristic, that is the current of the collector. This is the collector to emitter voltage. These are the base currents. And we see here actually two distinct behaviors. One here, which is the saturation region, at which the voltage across the BJT is very low. And then we have this region here, which is called the active region, in which the BJT behaves like a current source. The current is pretty much independent on the collector to emitter voltage, while here it's kind of dependent on it, and it's sort of a straight line here. So this will be the saturation region in the BJT, and this will be the active region. On the other hand, and it is really very unfortunate, the saturation region in a MOSFET is defined here. This is the saturation region. While this part here is defined as the ohmic region, this is sort of an expanded scale. If you zoom out, you'll find that this is almost a straight line, and we call this RDS on. This is the resistive behavior of a MOSFET when the voltage across it is very low. So there is a problem here in definition. This is called saturation, and here it means the voltage is very low and the transistor is in saturation. And here the saturation means that the channel, and I'm going to cover it in a minute, the channel is kind of saturated and is sort of sweeping the current, and the current is constant. So this is a source of big confusion, because here saturation is the low voltage, here saturation is the current source. So let me cover the operational regions of BJT and MOSFET. I'm starting with the BJT. The best way to understand the operational region is to look at the so-called Eber-Small model, which is this one. This is sort of mimicking what is happening in the semiconductor here. This is like a NPN transistor. This is the collector, emitter, and this is the junction here, the base. And here we have a diode, here we have a diode. So these are the two diodes. And as we inject carriers, charge carriers, they are swept. And this sweeping can be emulated by a dependent current sources, here and here. This current source, which is the forward current source, depends on the current here, while here, this reverse current source depends on the current here. So this is the very basic Eber-Small. So we have now the cut-off region in which there is no current, there is no conduction within the diodes, no injection of carrier, and therefore there's no current here, and of course these dependent sources are not invoked. And then we have the forward conduction. In the forward conduction, we are injecting current to the base, passing through this diode, and therefore this current source is now operational. We have a current here, we have this diode. So this is the very basic model of a transistor. These are non-operational because there is no current here. This diode is reversed bias, so there is no current here, and therefore this dependent source does not carry any current, which is the function of the current here, and there is no current here. So this is the normal operation, the linear operation of a BJT, and we see that this is a current source. Here is the current source. And then we have the saturation region. First of all, it has to be understood that saturation is invoked by the load. That is, what is causing saturation is the fact that you have a load resistance which is of high resistance such that the current is limited, and if the collector current is smaller than beta times the base current, beta being the current gain, then you enter into this saturation region. And in this saturation region, both of these diodes are conducting, okay? This one and this one. And therefore, the voltage you see here is the difference between the voltage drop on this diode and the voltage drop on this diode, okay? Here, this voltage here is the difference between this, and this is what you see here. If the currents will be exactly the same of the two diodes, then you'll see here 0 volt. This will be deep saturation. If the currents are a little bit different, then of course you'll see somewhat voltage higher than 0, depending on what's the difference of the voltage drop this diode and this diode. So let's have a look at a sort of extreme case. Suppose there is no current, or the current of the collector is very, very low. In this case, we inject here a base current. We have a current here circulating here. We have a current here. Because we have current in this diode, this current source is now carrying current. So we can look now at some relationships here. This is an extreme case. We see here that we have a current loop here. So this current is equal to this one. So here it is IB, I call this IB1 is equal to the forward alpha times IB2, here it is. And then I have that the current here is the difference between, or the sum, I should say, of IB plus this, okay? So this is the current here. Now, the current IB1 is alpha forward times IB2, this is this current source. These are equal. So we see that IB1 is somewhat smaller than IB2, okay? If it is smaller, then the voltage drop on it is a little bit lower. So therefore, the difference is such that we'll have a positive voltage here, depending on the difference between the voltage drop here and the voltage drop here. Now, IB2, as I've said, is IB plus this current, and working it out, I can find out that IB2, the value of IB2, is IB over 1 minus the product of these alpha. So this is the absolute value of IB2 as a function of IB, and this is the relationship between them. So as we understand, saturation in BJT is when the voltage is low and we have the conduction of the two diodes. Now, obviously, as the current of IC is becoming larger and larger, we'll see here a voltage which is going up. I'm not writing all these equations here. And then there is another option here, which is actually flipping the transistor over and sort of calling the collector as a new emitter and the emitter as a collector. So we are sort of flipping between the forward alpha and the reverse alpha. In most transistors, it'll work. Usually it is not symmetrical because the areas of the base of the collector and emitter are not the same, but still you can actually operate it. And as a matter of fact, when you do it, you get a saturation voltage which is lower. So in some application like choppers, it is rather customary to flip over the transistor. You have to check the transistor, of course, to see how it works when it is flipped over. So now I'm coming to the MOSFET. In a MOSFET, we have a channel that's not a bipolar. There's a channel. In this case, it's an N-type, say. It's a enhancement mode. We have a isolation, metal oxide. Then we have a gate. This is the connection to the plane of the gate. And then we have the source, the drain. Everything is sort of sitting on a substrate. Now, the cutoff situation is when the gate to source voltage is below the threshold, and then the field here is low, and therefore in the enhancement mode there is no charge carriers in the channel, so it's non-conducting, and this is when the transistor is in the off position. So this is the cutoff. So now if we apply a voltage to gate to source which is higher than the threshold, and if we are in a situation that the gate to drain voltage is also above the threshold. By the way, these are not exactly the same threshold. I'm assuming these are the same values. This situation appears when the voltage of the drain to source is low. So let's have a look at it. If these are the requirements, and then since V gate to drain is the voltage minus the gate to source, the total drain to source minus this voltage here, we come up with this condition that these two requirements are met when VDS is lower than VGS minus VT. So when the drain to source voltage is low, below this value, we have these conditions so that the two ends are inducing carriers, so therefore the channel is open. So the ohmic region is when both the gate to drain and gate to source are inducing carriers, and we have a conduction path through the channel which exhibits itself like a resistance here, which is the ohmic region. Now, if I increase the voltage of the drain with respect to the source, eventually I'll get to the point that the gate to drain voltage is lower than the threshold, and this happens when the drain to source voltage is larger than this same value we have seen before. So now this part here has no induced charges, and in fact it is like squeezed down, and we call it the pinch-off phenomenon. Now this pinch-off phenomenon now is sort of blocking, you might say, the current. There is charge here, which is a function of the value of VGS above the threshold. The larger the VGS, the more the charge. And what really happens is, at this point, at the pinch-off, the electric field is very large because it's a small area and the whole voltage drop is across it. So what really happens in an intuitive way, without going into quantum mechanics, the charges which are approaching this point are sort of swept over by this very high electric field that we have here. So now we have charges. There is an electric field here which is pushing them this way, and as they approach this pinch-off, they are swept off. So there is an amount of charge that is sort of moving toward this pinch-off point, which exhibits itself as a current source, which is dependent on the amount of charge that we have here. So this is now the constant current situation, and this is the saturation region. Saturation in the sense that the channel now is sort of saturated and there is the sweeping effect of the charges. So now back to the riddle. The question of the riddle was find at least 3 errors in the explanation of the articles or the tutorials in the website that I've mentioned. So let me start with the first article, and this is a section from this article. It says saturation region, and it is related to the MOSFET. It says when VGS is larger than threshold and VDS is larger than VGS. This is not correct. As we have seen, the exact expression is VDS is larger than VGS minus VT. This is for the saturation region. And then it says the transistor is in constant current region and is therefore fully on. Well, fully on, constant current, it's not fully on because it's fully on when it is like a switch. Here it is controlled as a current source depending on the value of VGS. And then it says that the drain current ID is the maximum with the transistor acting as a closed switch. This is definitely incorrect. In the saturation region, the transistor behaves as a constant current, not a closed switch. So I think there is a confusion here between saturation region in a MOSFET and in a BJT. In a BJT, the saturation region, this is where the transistor is behaving, acting as a closed switch. In the case of a MOSFET, this is a constant current. So this whole thing is just incorrect. And if you count, this is incorrect, and of course this is incorrect. So we have already here 3 errors. And then let's go to the second article. It says the following: saturation region. In the saturation or linear region, well, linear region is not the saturation region in a MOSFET. The transistor will be biased so as to maximum amount of gate voltage is applied to the device. Well, this is incorrect, of course. What does it mean, maximum amount of gate voltage? The voltage has to be above threshold and less than the maximum permissible voltage to the gate before it breaks down, which results in the channel resistance RDS on. This is not in the saturation region, this is in the ohmic region. And on being small as possible with maximum drain current flowing through the flowing through the MOSFET switch. Well, maximum is really depending on the resistor. It's not maximum in absolute value, but really limited by the resistor if it is acting as a switch. And this is what is shown here. If it's acting like a switch, it'll be in the ohmic region, which will be determined by the current and the value of this resistor. Because as the resistor is becoming larger, VDS is becoming smaller, and we enter into the ohmic region. And then it said the saturation characteristics, which should probably be ohmic. MOSFET switch saturation. The input and gate are connected to VDD. Well, yeah, connected to VDD. This is, of course, in some cases happening, like in ICs, digital ICs, but in general, this is, of course, incorrect completely because it could be damaging to the gate. This voltage could be much higher to the maximum permissible gate to source voltage. So you just don't connect it to VDD. You connect it to a voltage that will be high enough that is above the threshold. And then it says MOSFET is on, saturation region. Well, that's not saturation, that's ohmic region. Maximum drain current flows, which is VDD over RL. This is approximately, of course. You have to add here the RDS on. And it says VDS is 0. Well, if the resistance is very, very small, then this will be approximately 0. Minimum channel resistance is smaller than 0.10. Well, this is, of course, depending on the transistor. There are some transistors which high voltage transistor which will have RDS(on) of several ohms. So this is not correct in general. And then it says that V out VDS is about 0.2 volt due to RDS(on). Well, it could be millivolts, it could be volts. So this is just an example. And a MOSFET operates as a low resistance closed switch. This is correct if you're talking about the ohmic region, not the saturation characteristic. So counting now the errors, we have probably 8, something like that, plus, I mean, here it's, let's say 5 plus the 3. So we had quite a bit of number of errors. So this brings me to the end of this presentation. I hope you found it of interest, and I thank you very much for your attention.